Welcome on board. It's a nice week again. We are together for physics lesson. Well, welcome on board. My Form 3, Form 4 and Form 2 is based on the Form 3, but for the Form 4 it's a revision, and for the Form 2 it will be a topic ahead where they can get some experience. Okay, in our last physics session we ended with the application of the kinematic equations of the equation of motions, whereby in one of the application is whereby when objects move toward the gravity or against the gravity, and we saw how the kinematic equation changed, whereby the acceleration was replaced with the gravitational pull denoted by G. Maybe to remind you, I'll just do one question among the question I had left as an exercise. The second question was, a ball is thrown vertically upward with an initial velocity of 20 meters per second. Calculate the time taken to return to the thrower, and second, the maximum height. Okay, as when we started our physics lesson, I emphasized that I'll be using a four-step skills, whereby I can denote it as V, whereby the V stands for visualize. Before, when you are given a physics question, first you have to visualize by trying to draw a sketch of the problem. Then conceptualizing is whereby you try to find out from the problem what hints are you given, what known values are you given, so that will help you to find the unknown ones. Then analyzing is whereby we'll try to manipulate mathematically and to get the correct answer. And finalizing is whereby the answer will we'll try to ensure that we put the correct SI units or in the correct form. Okay, our sketch can be like this. This is our ball being thrown upward. This is the height. You can say this is for S. U, we have 20 meters per second. So our initial velocity is equal to 20 meters per second. Our G, we know is for this we'll use 10 meters per second square. The gravitational pull is 9.8 meters per second, but for approximation we usually use 10 meters per second square. Then when an object moves upward, the moment it reaches the highest or the peak, before it goes down, at that point the velocity or the final velocity is 0 meters per second, because before the ball will reach the maximum height, it will stop, and so when it stops, the speed or the velocity is taken to be 0, because it will stop momentarily and start going downward. So in our case, we'll see that we have the final velocity, the initial velocity, and the gravity. But we are asked about time. So in the kinematic equation or applied to gravitation pull, we have the equation as final velocity is equal to initial velocity, but for our case, since it is moving upward, it is going against the gravitational pull, it will be minus gt. So we'll try to make t the subject. So we'll see that gt is equal to u minus v over, we'll divide by g, so we'll get t is equal to u minus v over g. So we insert the values and we'll get our initial velocity is 20, t is equal to 20 meter per second minus 0 meter per second over the g or the gravitational pull, which is 10 meter per second squared. So when you subtract 0 from 20, you'll still get 20. So 20 meter per second over 10 meter per second squared. So the meter per second will remain with just 1 second unit, whereby t will be equal to 2 seconds. But we are asked the time taken to return to the thrower. So this is the time taken for it to reach the maximum height, but there's also the time from the maximum height back to the thrower. So approximately it will be twice this time, but we can still find it. We have our time. So we have the time upward. Seconds. So now in this case, we can proceed to the second question then we'll go back, because we'll have first to find the height. Then in our second portion of the first question, we'll now take the initial final velocity to be when it was going upward, the final velocity for when it goes down now becomes our initial velocity. So from the second equation of kinematics, we have distance is equal to initial velocity t minus a half times gravity times t squared. So in our first, when it was going vertically, our initial velocity was 20. So time is equal to 20 times t, whereby we have gotten our time for upward movement. So times 2. Let's put the units so that we don't be confused. Times time, which is 2 seconds, minus a half times the gravity, which is 10 meter per second squared, times time, which is 2, so it will be 2 seconds squared. So this will be the same as 4 seconds squared. The second squared will be 2, and here we'll have 5, so we'll have 4. Since the second square has gone, it will be 4 meters. Then here we'll be having 40. It will be 40 meters minus 20 meters. So we'll find that our distance or the height is equal to 20 meters. So from having find the height, we can now embark to the second portion of the first question, where we needed the final velocity. So from the third equation of the kinematic equations, we have final velocity is equal to squared is equal to initial velocity squared. Now it is going downward. So we insert the addition sign. So we don't know our final velocity when it's moving downward, but we know our initial velocity. So the final velocity squared is equal to 0 squared plus 2 times 10 the final velocity squared is equal to 0 squared plus, you can just put 0, 2 multiplied by 10 multiplied by distance, which is 20. So here we get, this is 200 times 2, which is 400. So V, or the final velocity squared, is equal to 400. So we find the square root, and we find that the final velocity, when it reaches back to the owner, it will be 20 meter per second. So from there, we have the final velocity, and we have the initial velocity when it was moving downward. Then we'll see that V is equal to U plus T plus G T, since now we are calculating for the time when it's moving downward. And now our final velocity, we have it as 20 meter per second is equal to 0 plus gravitational constant, which is 10 meter per second squared, times T. So we'll divide this other side, which will be 20 meter per second divided by 10 meter per second squared to get T. You'll see that still also for the downward movement, the time is also 2 seconds. So the total time taken for the ball to reach the thrower will be the 2 seconds for upward movement added to the 2 seconds for the downward movement, which you get 4 seconds. So it took 4 seconds for the ball to go to the maximum height and back to the thrower. Okay, to our today's session, there's also an important part which I'll need to discuss with. We have the components of vectors. We need to know how to find the components of vectors before we go into our today's session of the laws of motion. So we are told that in mechanics and other branches of physics, we often need to find the component of a vector in a certain direction. So the component is the effective part of the vector in that direction. So in our case, we are told to imagine or to consider the picture, a picture held by two strings. Let's say 6 Newton, and it subtends an angle here we have 60 degrees. So this will be 30 degrees. Okay. When drawn, so we'll see that this being the force, it is acting on an angle. So we have to find the effective parts of the force, the x component and the y component. So because since it is acting on at an angle, it has two components, both the x component and the y component. So when you draw like a rectangle or the representation of the force, we see that this being the angle and this the direction of the force. So this is the direction, this is OX and this is OY. So the representation of X and Y relative to the force, we'll see that from the trigonometric ratios, X can be represented. We'll see that cos theta whereby from the trigonometric representation we have the SOHCAHTOA, whereby for the sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So in our case, cos will have the adjacent, which is, this is our theta, this is the adjacent, and this is the hypotenuse. So we'll have x over f. Then we need to see how can we represent x relative to the force and the trigonometric ratio. We'll see that x will be equivalent to f cos theta. F cos theta. And this also, we see that sine theta is equal to the opposite over hypotenuse, where this is the opposite to the angle. This is it, which is equivalent to y. So sine theta is equal to y over f, the hypotenuse. So y is also f sin theta. So we are told that the component of any vector f in a direction making an angle theta to f is always given by the component f cos theta. So if a force is acting at an angle, so for its x component is always f cos theta. You identify the angle and its x component will be F cos theta. So it's like as if the force is acting this side and this way. Yes, it's shown only this way, but in real sense, it has two components. It's like it's pulling the picture on the x-axis line and also on the y-axis line. Then in a direction OY, this is the direction OY, perpendicular to OX, F has a component F cos. So this total is, this is a right angle which is 90. To get this angle is equivalent to 90 minus 30, whereby you see that for OY of cos 90 degrees minus theta, which is also equal to F sin theta. So when you are told to find the components of a force, you just have first to identify the angle and know how to represent that force in the x direction and also the y direction. Quickly, let's look into our today's session, which is the laws of motion. And also this component of vectors has an application Okay. In 1687, Sir Isaac Newton published a book called Principia Mathematica, in which he set out clearly the laws of motion. We have three laws of motion, which are usually referred as Newton's law of motion. They are usually used in Newtonian motion or Newtonian mechanics. So the first law of motion, or the first Newton law of motion, is, it says that a body continues to be in a state of rest or to move with uniform velocity unless a resultant force acts on it. It means provided no resultant force acts on an object. If an object is stationary, it will remain stationary unless a resultant force acts on it, so it will make it to move. And also, this is for stationary object. Then we have the second condition is if a body is in motion, let's say 20 meters per second, provided there is no resultant force which the motion will still proceed, provided no resultant force acts on it. So for the body to move, there must be a resultant force to make it to move, and for a body in motion, there must be a resultant force which will make it to stop. In our daily experience, we find that when we are in a vehicle and we are in movement, when the vehicle suddenly stops, makes a stop, we make that reluctant. We still want to proceed with the movement while the vehicle has already started. It also applies when the body or a vehicle is stationary. When it starts to move, you'll see that you will go forward and backward. So that reluctant to movement or reluctant to stop is known as inertia. So it is also referred to the law of inertia, whereby inertia Okay, we go to the second. The second law of motion said that the change of momentum per second is proportional to the applied force and the momentum change takes place in the direction of the force. The second law Newton's second law of motion states that the change of momentum per second is proportional to the applied force, and the momentum change takes place in the direction of the force. This is one of the most used equation in mechanics, whereby there are many versions of when you are asked to state the second law of motion, go through books and find the simplest way on which you can. When you are asked to state it, you have to get it directly from the books. So you can find a better version when you are asked in an exam, state the second law of motion, Newton's law of motion, you are able to state it. And also it's good to understand, because the terminologies used, they are not that strange to us. If you're a physics student, you have to know them. Whereby in our next session, we'll start from the second law of motion, whereby we'll try to elaborate it further and even to go into more examples and see how does it affect, or is it being applied in our daily life. I hope you enjoyed, and also you can go through the books. Where you find any difficulty, please try to comment, so that when I'll embark in our later session, I'll also consider your comments or interest. Thank you.